All right, welcome to The Explainer. Today, we're going to completely rethink one of the most basic ideas in math, the function. And we're going to see it not as some static graph on a page, but as a dynamic, living force that actually shapes the very fabric of space.
So, let's just jump right in with a question. We all learned that sine and cosine give you a circle, right? Simple enough. But what if there was one single, more powerful function that could also draw an ellipse and even a hyperbola, all just by twisting a single knob?
Well, the answer is a big yes. And that function, that mathematical master key, is called the elliptic function. Think of it as a huge upgrade to the trig functions we already know and love. It contains them, but it can do so much more. So how does this whole thing work? Well, check this out. The elliptic function has this little control knob, a parameter we call k. When k is set to 0, boom, you get your standard sine and cosine, drawing a perfect circle. Now, if you turn that knob anywhere between 0 and 1, the circle starts to stretch into an ellipse. And then, if you crank it all the way up to exactly 1, the function morphs again, becoming the hyperbolic tangent, and it sketches out a hyperbola. It's pretty amazing. One function, one parameter, three totally fundamental shapes. This idea of one function literally transforming into another, it hints at something much, much deeper. It's the gateway to a whole new way of understanding what a function is at its core. Look, in high school, we're all taught a function is basically a graph. An input x gives you an output y. But that's kind of like describing a hurricane as a windy day. The modern view is way more epic. A function is a dynamic transformation. It's a force that literally grabs a space, like the number line, and actively stretches it, folds it, and warps it into something new. To really get a feel for this, let's take an old friend. F of x equals x squared. Now, your first instinct is to picture a parabola, right? Forget the graph. For a minute, just forget the graph and think about what this function does to the number line itself. Okay, so picture this. You take the infinite number line. The function f of x equals x squared grabs it and folds it perfectly in half right at 0. So -1 lands on top of +1, -2 on +2, and so on. Then it starts stretching this folded line, but not evenly. It sends every point to a new spot that's the square of its original distance from the center. And that's the real takeaway. The function isn't a picture, it's an action. It's a physical manipulation of space. So if functions are these space-warping forces, the next logical question is, what happens when two of these forces act at the exact same time? Let's think about what it means to multiply two functions, say f of x and g of x. This isn't just some abstract thing you do on paper. It's one force interacting with another. So what does that even look like? Here's a really powerful way to visualize it. The second function, g of x, creates a kind of a modulating environment for the first one. It acts like a boundary or an envelope that contains and shapes the behavior of the first function. And you've actually seen this in the real world, maybe without even realizing it. Just think about AM radio. You've got this high-frequency carrier wave, that's our f of x. It's just a pure, boring tone. Then you have the sound of my voice, that's our g of x. When you multiply them, the shape of my voice becomes the envelope that squeezes and shapes that carrier wave. That's the signal that goes out over the air. My voice literally created the environment for that carrier wave. Okay, so if one function creates an environment for another, what happens when they are, in a sense, perfectly immune to each other? This brings us to a super important idea in math called orthogonality. Now, there's the formal definition, that scary-looking integral equals 0, but let's just focus on what it feels like in this new world of forces. It means that when that environment function, g of x, acts on the signal function f of x, all the distortions it creates, all the stretching, all the shrinking, all the flipping over a certain interval, they all perfectly cancel each other out. The net effect is absolutely nothing. It's like the two forces are in perfect balance. They're completely independent of one another in that space. This whole idea of behavior gets even cooler. You can start to think of some of the most famous, complex functions as having their own distinct personalities, defined by the unique ways they relate to themselves. Let's meet two of the heavy hitters, the gamma function and the zeta function. The gamma function's whole personality is about sequential evolution. It builds itself one step at a time, kind of like a staircase. The zeta function, on the other hand, is all about symmetrical reflection. It defines itself by staring at its own reflection in a mathematical hall of mirrors. And you can see these personalities right in their DNA, in their defining equations. Look at the gamma function. Its value at some point z plus 1 is defined by its value at the step right before it, z. Classic staircase behavior. Now look at the zeta function. Its value at some point s is directly tied to its value at 1 minus s. Its perfect reflection across a critical line. That's the hall of mirrors. They're both talking about themselves, just in totally different ways. So, this entire journey, this new perspective, brings us to our final and maybe most mind-blowing realization. If functions are all about transforming space, then what does it actually mean to find a root or a zero? We have to ask a totally new question now. In a universe built on bending and warping space, what on earth is a zero? Because the old answer, it's where the graph hits the x-axis, that just doesn't cut it anymore. That tells us what it is, but it doesn't tell us why it's important. Here's the deeper answer. A root, a zero, is a point of return. It's a special, magical input where the transformed space, after all the folding and stretching and warping, finds its way all the way back home to its original, fundamental, undistorted state of zero. You can think about it a few ways. It's an equilibrium point where all the transformative forces just perfectly balance out. It's also closely related to a fixed point, a spot that doesn't move at all. But maybe the most powerful way is to think of it as home base. It's the one input that sends the warped space right back to the origin.
And get this entire way of thinking completely reframes one of the biggest unsolved problems in all of math. The famous Riemann hypothesis? It's really just a very specific, very bold prediction about exactly where all of these special return-to-origin points for the zeta function have to be. It's a treasure map to the function's points of perfect balance.
And that just leaves us with one last, kind of wild thought to chew on. If the physical laws that govern our universe are all described by functions, these grand transformations of space-time, then could the fundamental constants of nature be the zeros of some massive cosmic function, the unique points where all the forces of reality find their perfect final equilibrium?